questions about anything at all before we go? Those are all right. Just a remind, Tuesday is advisory day, and all that doesn't affect our schedule here for class. We want to remind that we'll have pizza in the past week on Tuesday, so stop by and eat pizza. I did put a due date in for the stuff that we're talking about today in the web assign. We started last time, we talked about more today. Hello.
Hello.
So the stuff that's on the row space, column space, null space section, I think it's section 4.6 in the textbook, will be due on Tuesday in web assign. I graded it. Somebody else. All right, so the homework over section 4.6 in web assign will be due on Tuesday. And then you've got other homework that's due on Monday. Thanks. I forgot what day it was. All right. Well, let's continue on then our discussion here with row space, column space, null space stuff. So last time we talked about the different definitions. Go back and scroll up here to the top. So remember we had all those definitions of row space. That was the space, the subspace of Rn that we formed by considering the rows as vectors and looking at the set of all linear combinations of the rows. Column space, we do the same thing, except we treat the columns like they're vectors in Rm and do the set of linear combinations of those things. Null space is the solution space to the associated homogeneous system. And then rank is the number of pivots that you get in the reduced row echelon form. It also turns out to be the dimension of your row space and the dimension of your column space. You can go ahead and turn that off again so I don't have to shout over the top of it. I'm loud enough, but I feel like I'm shouting now. Thank you. The rank is your dimension of your column space and your dimension of your row space. And then the nullity is the dimension of the null space. All right, so just to remind us of those definitions that we talked about last time. So talked about various concepts last time, how we find the different bases for these things. Pardon me, goodness. But let's talk about some of the relationships among these different things. So how about the transpose of a matrix? Well, we know when we transpose the matrix, we take the rows and make them into columns, and the columns and make them into rows. So how could you relate the row space of the transpose? What's that going to relate to? In terms of the original matrix A, what's it going to relate to? The column space, right? And likewise, the column space, pardon me, the column space of A transpose will be, yeah, the row of the original. Good. So that's just some of the relationships between the transposes of the different things. But remember, pardon me, that the rank of the original matrix tells you what the dimension of the row space and the dimension of the column space are, and they're equal to each other, right? So if the rank, if the dimensions of these two things are equal to each other, of the column space and the row space of the original, if those dimensions are the same, what can I say about the dimensions of the row space and the column space of the transpose? Those are also the same, right? Well, if these are the same and are equal to the rank of A, these are the same and are equal to the rank of A transpose, what can I say about the rank of A and rank of A transpose then? They're equal to each other, right? So that's a result of these two things, together with the fact that we know that all the ranks are equal. This all tells us that the rank of A transpose is the same as the rank of A. So thinking about it in terms of row reduction again, if I row reduce A put it in reduced row echelon form, the number of pivots that I see in the reduced row echelon form of A is the same as the number of pivots that I see when I row reduce A transpose. Even though they're going to have different dimensions. Well, if they're square, they don't have different dimensions, but in general, they have different dimensions, right? So even though it's not horribly surprising, it is kind of interesting that even when I flip-flop the dimensions, I still get the same number of pivots. So the rank stays the same. The rank doesn't change at all. Now, of course, the nullity would change, maybe, right? But remember, nullity is the dimension of your null space. That has to do with the number of free variables that you get when you row reduce, right? Right? Okay. If you row reduce, you may, if I change the number of columns, I might change the number of pivot-less columns, right? Even though the number of pivots won't change, if I don't have as many columns as I started with, I would have fewer free variables. If I have more columns than I started with, I'll have more free variables. So it might change, the nullity might change when you take a transpose. The dimension of your null space might change. But your dimension of your column space and your dimension of your row space will stay the same. So the rank stays the same. Okay. All right. Pardon me. Goodness. So I actually will write that down. The nullity of A transpose most likely will change. So I was right, is not necessarily the same as the nullity of A. If A is not square, they most assuredly will not be the same, because the number of columns that you're dealing with will be different in the two matrices. And the number of pivots that you have in a reduced row echelon form will be the same. So it'll change the number of free variables that you have. The number of pivot-less columns. All right. The next relationship we're going to talk about is just how does the number of columns of the matrix relate to rank and nullity. So again, your dimension, your rank, let's try it this way. Your rank is the number of pivots that you have. Your nullity is the number of pivots that you don't have, right? If I add those two numbers together, I have to get the number of columns in my matrix, right? So your rank is number of pivots in columns. Your nullity is pivot-less columns. Add those two together, you get the number of columns. So that's the relationship we're looking for here. So if A is an M by N matrix, then the rank of A plus the nullity of A is equal to N, the number of columns of A. That's an N, even though it looks like, I don't know what that looks like. Sanskrit maybe. This is sometimes referred to, shockingly enough, as the rank nullity equation. It's pretty aptly named, I suppose. All right. And then this last part here is literally what we were just talking about. For your dimensions of your spaces, we know that the rank, I think we've already written this down, but I'll write it down again. So again, your rank of your A, I wrote this down earlier in the previous the sheet that we talked about last time. But your rank is your dimension of your row space, which is also the dimension of your column space, just so you have it all in the same spot. And your nullity is the dimension of the null space. Just a reminder of what we talked about yesterday. Not yesterday, Wednesday, whatever day. Previously. last time on linear algebra. We also talked about the next bit too. But are we okay with these concepts here? So again, the most interesting part, I think, is the first part, that when you transpose a matrix, it doesn't change the rank. Of all of that, I think that's the most interesting part. However, if I do transpose a matrix, it probably changes the null space. Now, it will actually change the null space, unless it's a symmetric matrix, and then it won't. But it probably will also change the nullity. This is good true-false question fodder here, by the way. The content, what the concepts that are going on. This is a good true-false idea. So make sure you're thinking about these and what they say and what they don't say, because you can change things easily and make true-false switches. Like for example, this one here. If I change that n to an m, it would be false. I can change it pretty quickly. So just to kind of give a little precursor for the exam in a couple of weeks. All right. So we also talked about this last bit. Again, let's suppose that our A here, just to make sure that we just use the numbers that we're talking about. Let's suppose that A is an m by n matrix, just so I can refer to the m and the n. We talked about this first part last time. If that system is going to be consistent, so if I'm talking about the system AX equals B, if that system is going to be consistent, if I augment the B on the end, should I get a pivot in that very last column or not? If it's going to be consistent, do you want a pivot in the constant column? Okay, remember, if I have a pivot in the constant column, what's the last row going to look like? It'd be a bunch of zeros here and a 1, right? For consistency, pivots in constant columns are bad, right? So what happened to the rank, if it's inconsistent, what happens to the rank of A if I augment the B on the end? Does it stay the same or does it go up? It goes up, right? So if it's not consistent, the rank goes up, right? So we talked about that last time, pardon me, that your rank of A is equal to the rank of A augmented with B if and only if AX equals B is consistent, right? We also said that if AX equals B is consistent, then we know we can write the vector B as a linear combination of the columns of A, which means that B lives in what space related to A? The column A. Good. It's in the column space. Good. So this is also, if I want to do another equivalency, this is also if and only if B lives in the column space of A. Again, if you augment a vector to the matrix and the rank goes up, then it can't be in the column space, right? Because remember, when we, for example, when we tie it back to stuff that we did for linear independence, remember for linear independence, we went back and picked out the columns that had pivots in them. That was how we found the vectors that were the form linearly independent set. If I put a pivot in this column, I would pick that particular vector to be one of the linearly independent ones in my set. Linearly independent means it doesn't depend on the others. It can't be written as a linear combination of the others, which means it can't be consistent. So tying that back to that idea as well. All right. So again, as far as consistency is concerned, pivots in the last column and the augmented column are bad. We don't want to pivot there. So how about how the rank and span goes? So remember span when you do the reduced row echelon form of the matrix. How do you check for span? What do you look at? Pivots in every row, right? So if your rows span Rn, so remember your row vectors are in Rn, then what can you say about, oops, then, not than, what can you say about the span, the rank of A related to the size of A? What does the rank have to be? You just told me that it's going to span everything. We need a pivot in every row. All right? Gotta be careful here. So what I want to say. Span R. I'm saying the wrong thing here because that's not what I mean. I need a pivot in every row for if the set of vectors, but remember how I'm writing the wrong thing. I should say the columns. I'm writing the wrong thing. Sorry. Go back. Let's go back to this. If the columns span R, it's not how you spell column. If the columns span RM, remember that's how we check for span. We want to pivot in every row, but we take the vectors and make them into columns in the matrix, right? That was how we use check for span or linearly independent, right? You take the vectors and make them columns, right? So I want to look at what's going on with the column vectors. If the columns are supposed to span all of RM, then what better the rank of A be? M. It better be M, right? Okay. I better make sure that I hit everything, because remember the dimension of RM is M, right? So when I pivot every row, I better make sure that I have the rank of A being M. So if the columns are going to span RM, then I better have rank M. Okay. Let's go the other way. If the rows span Rn, what would we need? Well, let's think about it. If the rows are going to span Rn, I'd have to think about it the other way. Again, if we're checking span, this is where I was getting, where I was not thinking correctly to start this off. If I'm thinking about checking span, again, I make a matrix and take the vectors and make them into columns, right? Well, if I want to check if the rows span Rn, I would need to make a matrix and take the rows and make them into columns. How do I take rows and make them into columns? Transpose, right? Okay. So I want the rank of A transpose to equal what then? If I want to take these rows and make them into columns, I take the transpose. I would want the rank of A transpose to equal N, but the rank of A transpose is the same as the rank of A, right? So if I want the rows to span Rn, then I need the rank of A to be N. I got ahead of myself when I started writing this down. All right. So it also, goodness gracious, why am I having trouble clearing my throat? It also works the other way. If the rank of A is M, then the columns span Rm. If the rank of A is N, then the rows span Rn. That's how those relate. All right. Consistency and linear independence. So let's think about, again, what it means to be consistent. Let's think about just the matrix in general. And if it's going to be consistent, what's going to happen with your, pardon me, your matrix? Okay, so again, we have the matrix A, and we want to augment it with B, right? If we row reduce and you end up with something that looks like this, we know that it's inconsistent, right? We've talked about that several times, not including like the last 5 minutes. Okay. All right. So again, when we augment, we don't want the rank to go up, right? One way to guarantee the rank doesn't go up is that I make sure that I have a pivot in every row to start with. And then if I augment another matrix, I don't get extra rows. I get extra, if I augment a vector, I don't get extra rows, I get extra columns, right? So if I already have a matrix where the rank of A is all of the rows, if it's equal to M, then it's always going to be consistent no matter what, correct? Does that make sense? If I already have a matrix A that has M rows, so if the reduced row echelon form of A has a pivot in every row, then adding B, or I shouldn't say adding, I should say augmenting. Augmenting B does not add an extra pivot. Okay, I don't get an extra pivot by doing that. So what that means is that if the rank of A is M, then the system AX equals B is consistent for all B. And that B would be in RM. So if I have a matrix where the rank is equal to M, right? If I have a matrix where the rank is equal to M, then I know I don't run out of pivots. Or I already know that if the rank of A is M, the columns span RM. We already know that. Okay? So I can't find anything that's not in the column space, which means I can always solve this system. If the rank is too small, if it's smaller than M, then I know that when I do the reduced row echelon form of A, I get a row of zeros, right? So you can find a vector that you can augment where I would have a pivot that ends up being in that bottom row in the augmented column, which causes it to be inconsistent. So if my A has a rank that takes up all of the rows, then I know that this is going to be consistent all the time. That's the important part. Okay. All right. So how does that deal with the linear independent part? Okay. How do we get to the linear independence part here? Well, let's think about it for a second. If it's not linearly independent, let's work the other way. Linear independence means that it is a pivot in every column when we row reduce, right? So how would you get something that would be inconsistent? Where am I trying to go with this? How would we get something that would be inconsistent? Well, you find linearly independent things that are inconsistent. What was I doing with this one when I made this up? Now I'm thinking about it. Because this is the important part that I want here. Might be talking about the transpose. Anyway, this is the important part that I want to talk about anyway. Is the fact that if the rank is M, then it is consistent all the time. I want to get to the equivalence parts. But anyway, this is the important part that I wanted to talk about. That if the rank, when you row reduce A and you get a pivot in every row, this is stuff that we've already talked about with systems of linear equations anyway. You get a pivot in every row. I can't add pivots because I've run out of rows. So it's going to be consistent all the time. And this is just rephrasing that in the language of rank. Anyway. Let's go back to, I mentioned this last time. Let's go back to the mega theorem and see if we can start adding equivalent conditions to being invertible. That was our mega theorem. What letter did we leave off at?
We were on number 7.
We were on number 7? Are there numbers? Okay, so number 7 is the next one. Is that right? Okay. All right. So, thinking about this now in the language of all the stuff that we've been using, we already said that if the matrix is invertible, then the reduced row echelon form has to be the identity matrix. Well, if the reduced row echelon form is the identity matrix, that gives us a pivot in every row and a pivot in every column, right? If the reduced row echelon form is the identity matrix, we get a pivot in every row and column. Pivot in every row tells us what? Span, right? So we know that number 7 tells us that the rows of A span Rn. Number 8 would also tell us that the columns of A span Rn. Oops. If I take my matrix and do the reduced row echelon form, I get a pivot in every row, which tells me that, well, that tells me, let's do pivot in every column. You pivot in every column, that tells me that the columns span all of Rn. Pivot in every row would tell me when I do the transpose, I would get a pivot in every column for the transpose. So then those columns in the transpose span Rn, which means the original rows span Rn. Okay? Pivot in every row tells us span. Pivot in every column tells us linear independence, right? So 9 is the rows of A are linearly independent. Number 10, the columns of A are linearly independent. Well, if you put linear independence and span together, what kind of thing do you get? The basis, right? So these all together tell you, for 11, the rows of A form a basis for Rn, and number 12 tells you that the columns of A issue for a basis for Rn. Why can I not spell columns today? I keep forgetting the N. Did it up here? Well, this one's a little messier. Oops. What a U, not an O. Anyway, can't spell today. It's fine. It happens. All right. So we've got these, and again, these are all equivalent to each other. And again, they end up being equivalent because of the size of the matrix, right? It's a square. So we've got these things. We can also phrase this in terms of rank and nullity. And row space and column space. If the rows of A span Rn, then what does the row space of A have to equal? If the rows of A span Rn, then what does the row space of A have to equal? Rn, right? It doesn't equal everything. So an equivalent condition here is also that the row space of A is Rn. Likewise, what do you think? Can you say about the column space of A? Also Rn, right? What's that going to tell us about the rank of A? It's n, right? Because remember, the rank is the dimension of the column space or the dimension of the row space. The dimension of Rn is n, right? So the rank of A is n. If the rank of A is n, what does that tell you about the nullity? It's 0. Good. Because remember, the rank plus the nullity have to give you the number of columns. The rank took up all the columns. There aren't any columns left for free variables. So we added a few equivalent conditions to being invertible today, didn't we? Went from 6 to 16. What I call it mega theorem. There's lots of things that tell you something is invertible. All right. So this is actually a nice summary for kind of the chapter, if you will. Any questions on that at all? This time together, I know it would take a little bit of time to assimilate it all, but it's okay. Yeah, that's no properties related to the null space or no particular properties. Yeah, if you want, the null space would be just the 0 vector. I can do that too. That's probably a good one. I can add that one. Sure. Might as well add it. The null space of A is just the 0 vector. That's a good one. One I probably would have added later when I realized I didn't include it. So thank you for that. Yep. The only thing, if the nullity is 0, the only thing that's in your null space is the 0 vector. And then we're going to tie these ideas later on to linear transformations here in a couple of chapters. Other questions on that at all? There's one brief thing that we didn't talk about. Well, we've actually talked about it, but didn't talk about it. And that's the idea of being coordinates relative to a basis. So I want to do a couple of examples of that before I go on to new stuff today in the next chapter. So I'm just going to keep writing down here at the bottom of the page. So on your last homework, you were given, I believe it was number 5, where the first thing you were asked to do is find a basis for the subspace that was described. And then the very last part said, find a linear combination of the basis vectors that gave you another vector. This was the very last problem on homework that I just gave back to you. Okay. All right. So that idea is actually coordinates relative to a basis. So let's just do a couple of examples of these. All right. So let's say we have, let's let S be the set of vectors. We'll do 1, 0, 0, 2, 2, 2, 2, 0, and 3, 3, 3. And we're asked to find the coordinates of the vector 2, negative 1, 3 with respect to this basis. So I'm telling you that this is a basis, but if you were to check whether or not it really was a basis, what would you do? Yeah, take it, make a matrix of those as columns and do it by the reduced row echelon form, right? So we check all of those. Yeah. So if I do that in this case, how do I know that I'm not going to close that off because I'm going to just use the same matrix to do what we need to do. But if I were to row reduce this, how can I look at that and tell me that it's going to definitely have a pivot in every column? And it's triangular, right? And I have non-zero entries on my diagonal, correct? So I can make each of those a pivot. It's triangular. I can tell it's going to row reduce to the identity matrix without doing any work. Okay. All right. So if we want to find coordinates of the vector relative to this basis with respect to S, well, we're going to do what we always do. I'm going to find, basically it's just asking you to find a linear combination of the three basis vectors that give me this. That's all it's asking you to do. Okay. So if we row reduce this one I'm not going to take the time to put into calculator because I can tell the last row, if I divide both sides by 3, I get 0, 0, 0, 1, 1, right? And then over here, let's see, what would you get? If I put in, that's a 1, 3, subtract over negative, I get negative 2, it looks like. Oops. Negative 4, negative 1, so I get a 3 here. Assuming I did my arithmetic correctly. Okay. This is stuff we've done before, right? So if you were asked to write this as a linear combination, how would I write my V as a linear combination of those three vectors? What would you use? Do you really mean row? You mean the, yeah, right, because it's 3 times the first minus 2 times the second plus the third, right? That's how we do that, isn't it? Okay. So this is 3 times 1, 0, 0 minus 2 times 2, 2, 0 plus 3, 3, 3, right? I'll even write the 1 times it. You did this on the homework, right? I hope you did this on the homework. Yeah. Okay. All right. So that's how we write it as a linear combination. When it asks you to find the coordinates relative to the basis, all it's asking you for are those coefficients. Now, we wrote this particular basis as a set, but when we want to do coordinates relative to a basis, we actually want to make sure that we pay attention to the order of the things in the set. We refer to that as an ordered basis. Because, for example, if I write the point 3, negative 2, 5, that means x is 3, y is negative 2, and z is 5. That's in an order, right? I don't want them to be mixed up, correct? So if I have my S written this way, and I form my matrix this way, then this coefficient refers to the first thing in my set. This coefficient refers to the second one. The last one corresponds to the last one, okay? So when we want the coordinates relative to that basis, we just pick off those coefficients. The notation looks like this. So you write the vector and then write a subscript S, and then you just write it as an ordered triple in this case. 3, negative 2, 1. So when I write it this way, I'm assuming I know what the order is in my basis, and it tells me I do 3 times the first minus 2 times the second plus the third gives me that vector. That's what the coordinates relative to the basis means. Oops. Let's do another one, but not things that are necessarily RNs. Find the coordinates relative to the basis S equals 1 plus x, 1 plus x squared, x plus x2, or x plus x squared, for the polynomial p equals 2 minus x plus x squared. What space am I probably talking about with these vectors? What space are we living in? I'm talking about these particular vectors that we have written down. P2, right? Dimension of P2 is 3, and I have 3 vectors in my set. It has the right size, but we would still want to check that it really is a basis, correct? Yeah. It's not too hard to check that it is a basis, but we would want to make sure that we really do have a basis. This is a basis. All right, so again, all this means is find a linear combination of these 3 things in this order and then pick out what those coefficients are. Okay? So how are we going to find a linear combination that gives us the 2 minus x plus x squared? What are we going to do? Instead of a matrix, that's what I would do. Yeah, make a matrix, right? What's the first column of your matrix going to be? 1, 1, 0. Second one will be 1, 0, 1. Third one will be 0, 1, 1. Last column will be, good, yeah, 2, negative 1, 1. Row reduce it. Let's see Ian type it up, so I'll wait for him to tell him what the answer is. What was the last? Just tell me the last column. I got it. Yeah, so that's 0, 2, negative 1. All right. So again, in the notation here, the notation is I take whatever the vector is, put it in parentheses, and then write the subscript here. That's just the notation we're going to use for this. And again, we will write this as coordinates. First coordinate we'll use is 0. Second one will be 2. Last one will be negative 1. Yeah. Basically, this is shorthand notation for writing it as a linear combination. It also gives us kind of an identification, right? This gives us an identification of this space with a 3-dimensional vector in R3. Really have an identification here, issue here. That's okay? All right. So if we did, well, we could do this for anything. So without having to type it all into a calculator, we'll just set it up. Let's say we look at matrices here, 2, 0, negative 1, 3, negative 1, 1, 0, 0, 1, 1, 0, 0. Whoops. Sorry, I put the, no. Do it this way, it's fine. And 0, 0, 1, 0 of the matrix, 0, 0, 0, 1. What space here do all your vectors live in? Yeah, the 2 by 2 matrices, M22, right? Dimension of that is 4, right? Because it's the 2 times the 2, right? Yeah. So there's 4, and so we do have the right number of vectors in our basis, right? Again, that doesn't check that it is a basis, but we know right away we can't just throw it out that as not being a basis. What would we set up now to help us solve? What would our matrix look like? It'd be 4 by 5 because I would have to augment that last thing on there. Yep. What would you use for your first column? 2, 0, negative 1, 3. As soon as I write it that way, I better do the other ones in the same exact order, right? So the next one would be negative 1, 1, 0, 0. The next one would be 1, 1, 0, 0. The last one would be 0, 0, 1, 0. And then your final column will be 0, 0, 0, 1. So how many coordinates would we end up with in this case? 4. And we should end up with 4 coordinates because there's 4 elements in my basis. The dimension is 4, so there should be 4 coordinates that we're dealing with. Did you happen to find them when you the last one, Ian, or did you get it typed in? If not, it's okay. I was just asking if you had it done. Okay. Anyway, at this point, you would do row reduction, and then you would pick out the coefficients at the end. The last one would be a third. Sorry, the first one should be a third. You'll definitely need a third of the first one. This is the only one that has anything in the last row. Right? So I definitely need 1/3 of the first one. And that one will be adjusted off of that. Is that okay? You think you can finish that one off? All right. So that's what we mean by coordinates relative to a basis. So, all right. This pretty much finishes up all of the stuff that we're going to do in chapter 4. So we'll get started in chapter 5 on Monday, which will start talking about inner products. I believe I posted an introductory video into inner products on Moodle. So if you want to watch that over the weekend to get kind of a head start on what we're going to talk about. I think it's like 13 minutes long is all. This should be able to be posted on there. So anyway, have a good weekend, everybody. We'll see you on Monday.